Hey everyone, and welcome to today's Explainer. We're going to be focusing on one of the most absolutely critical external interfaces in the entire transport network, the exact point where everyday public life meets the railway. When we think about railway safety, it's super easy to just picture the trains themselves, right? But a massive part of railway control extends far beyond just moving those huge pieces of rolling stock. It's fundamentally about how the railway interfaces safely with external public stakeholders. Okay, let's dive right into this because it is a fascinating, high-stakes engineering challenge. Just think about the sheer physics involved here for a second. You have a train, which can weigh thousands of tons and take literal kilometers to stop, intersecting directly with road vehicles and pedestrians, entities that are entirely, well, unpredictable. The inherent dangers of these intersections are just immense. Managing this conflict isn't just about throwing up a warning sign. It requires a highly dependable, rigorously tested safety architecture. So, to break down exactly how this works, we're going to explore 5 distinct layers of defense. First, we'll look at the level crossing interface itself, then warnings and physical barriers, followed by advanced obstacle detection, emergency communication networks, and finally, supervision and monitoring. All right, kicking things off with part 1, the level crossing interface, which is absolutely the high-risk zone. You see, railway control and communication systems don't just operate in a vacuum. At this specific intersection, the tightly controlled, hyper-regulated environment of the railway is suddenly exposed to the totally uncontrolled Wild West of the public roadway. It's the exact spot where road traffic, pedestrian pathways, and railway operations all crash together into one localized point. So, the heavy infrastructure we rely on is part of a deeply integrated control system, all designed to keep unstoppable trains and unpredictable cars safely apart. Because the risk is so incredibly high here, the railway relies on multiple safety nets. We call these layers of protection. We would never rely on just one single system to prevent a disaster. Instead, we stack them up like a fortress. We use engineering controls for warnings and barriers. We back that up with automated intelligence to detect obstacles. We provide direct lifelines through communication networks just in case things go wrong. And we wrap the whole shebang in overarching oversight through human or automatic supervision. Moving smoothly into part 2, warnings and physical barriers. These are our primary engineering controls. This right here is our first layer of active defense. The engineering controls deployed at these crossings form a highly dependable safety logic. And the main objective is vital. Literally stop all road and pedestrian traffic before the train even gets close to the intersection. A key component of this is something you've probably seen a million times, the wig-wag. I know, it sounds kind of funny, but it's a road traffic light signal featuring twin flashing red lights to warn you of an approaching train. And let's be clear, it's not a suggestion to yield, it is an absolute stop signal demanding immediate compliance. So how does this sequence actually play out in real life? It's a beautifully precise chain of events. Step 1, advanced train detection equipment, which is placed way down the track, senses the approaching train and triggers the system. Step 2, the wigwags begin to flash and those loud, audible alarms start sounding, giving everyone that crucial initial warning. Step 3, after a set time delay, the physical barriers descend to physically block traffic from entering the danger zone. Depending on the setup, these can be full barriers closing the whole road, or half booms blocking just the oncoming lanes. But one size definitely does not fit all. For example, a dedicated pedestrian crossing might just use fenced maze gates to naturally slow people down, essentially forcing them to stop and look for trains. Contrast that with a full road system where you need heavy-duty barrier booms to physically deter cars and trucks. The specific engineering control is always completely tailored to the specific type of traffic using that particular crossing. All right, let's look at part 3, advanced obstacle detection. This is where automated intelligence steps in. So, we've dropped the booms and the lights are flashing, but let me ask you a rhetorical question. What happens if a vehicle stalls on the tracks exactly as those barriers drop, basically trapping it inside the high-risk zone? It's a terrifying thought, right? Well, this is where automated intelligence comes to the rescue. Modern active crossings increasingly use advanced radar and LIDAR technologies to actively scan the crossing deck. The system doesn't just blindly assume the tracks are clear because the barriers are down, it positively confirms the area is completely free of people or cars before it ever allows the train's control system to clear the signal. This represents a massive, game-changing evolutionary leap in safety. Compare this to older passive crossings. At a passive crossing, the burden of safety is entirely on you, the user. You have to stop, look, and listen for trains yourself. An advanced active crossing totally flips that dynamic. It uses engineering controls, radar, and LIDAR to ensure high reliability and automatic safe operation. It takes the heavy lifting of safety analysis away from us sometimes flawed humans and gives it to highly dependable technology.
Which brings us to part 4, emergency communication networks. These are our direct lifelines.
Because let's be real, what if the technology fails or a totally unforeseen emergency occurs? We always have to account for the human element. This is our third layer of protection, designed specifically for those heart-stopping moments when immediate, manual human intervention is required to prevent a disaster. The core of this lifeline is the Public Emergency Telephone, or PET, located right there at the crossing. This phone is a direct line to the railway signaler, giving the public a fighting chance to halt approaching trains in a true life-or-death emergency. Now, when someone picks up that emergency phone at the crossing in a panic, where does it actually ring? It rings at a device called a concentrator. The concentrator is the operator interface sitting inside the signal box. Its entire job is to funnel the potential chaos of the outside world, from line-side phones, emergency calls, and adjacent control rooms, into manageable, actionable alerts for the signaler who is managing the railway. What's really fascinating about this setup is that the concentrator is explicitly designed to help signalers prioritize during a crisis. Imagine trying to monitor dozens of crossings at once. So it uses distinctive ringing sounds for specific high-risk crossings, meaning the signaler instantly knows it's a critical emergency just by the tone. It also uses flashing lights or dynamic displays to immediately identify exactly where the caller is. Modern IP-based versions even utilize these intuitive touchscreen dealer boards, ensuring the signaler can take rapid, life-saving action without fumbling around with clunky, outdated hardware. And that leads us to our final section, number 5, supervision and remote monitoring, the overarching oversight. So we have the physical barriers, the radar, and the emergency phones. But the final layer of our fortress is the overarching oversight that ties all of these amazing systems together. This is the absolute nerve center of operations, the signaler's workstation. Surrounded by monitors and communication interfaces, the signaler maintains constant situational awareness. For manually supervised crossings, they actually use CCTV to visually monitor the crossing deck in real time, literally checking for stragglers before manually issuing the command that the crossing is clear and safe for a train. However, there's a pretty distinct difference in how this oversight is applied depending on the railway's technology level. In manually supervised crossings, as we just mentioned, you rely on the signaler using CCTV to make a visual confirmation. In contrast, fully automatic operations, especially on modern or heavy-haul railways, rely on incredibly sophisticated predictor technology. If automated obstacle detection spots an issue, the system bypasses human reaction times entirely. It can automatically revoke the train's movement authority, triggering an emergency brake intervention miles and miles down the track. So what does this all mean? The absolute crucial point here is that regardless of whether a crossing is manually supervised or fully automatic, the ultimate goal remains exactly the same. We deploy these multiple, overlapping layers, the engineering, the detection, the communication, and the supervision, to create highly dependable safety features. We want consistent warnings and ironclad fail-safes that virtually eliminate the catastrophic risks associated with human error and misunderstanding at this super-critical interface. But the landscape is shifting rapidly. As we look to the horizon, a massive question remains. As artificial intelligence, advanced 5G communications, and self-driving vehicles become an everyday reality, how are they going to transform this high-risk intersection? Could autonomous vehicles eventually communicate directly with the crossing, enforcing an automatic brake in your car if a train is approaching? Could AI eliminate crossing collisions entirely? It is a fascinating frontier for railway safety and definitely something we'll be tracking closely as these technologies evolve. Thanks so much for joining me on this explainer today. Keep learning and stay curious.